A great pleasure to welcome Adina Goldberg. Adina has also been with us from the beginning of the program, and today she will talk to us about synchronous forms.
Hi everyone. It's really great to be here. So Moritz said in his talk that we weren't necessarily wanting to hear any more about quantum graphs today because we've already heard a lot, but I'm sorry to say you might hear a little more about quantum graphs today. So this is based on a preprint. So also as Moritz said in his talk, I didn't know there would be so many connections. When we try to quantize classical objects, there are sometimes a lot of different ways of looking at the classical object that will give us a different good definition in sort of the quantum version of things. And just from being at this workshop, I've learned that there's actually many approaches to quantizing either the questions or the answers or both of non-local games. I haven't cited them on these slides because they're older slides, but there are many. There are several at least. And so before I knew about all these definitions, I asked myself, okay, non-local games have these classical questions and answers. And in order to get to like a version of quantum games with quantum questions and answers, I first have to ask myself, how should I think of a classical non-local game? Like what version of it am I going to quantize? And so the way I decided to do it was to think of sets operationally, and I'll say what that means, okay? And then that gave me some string diagrams that I can reinterpret after doing all the definitions classically. I can just take the same diagrams and say, well, this is what I mean by quantum games, quantum strategies, quantum correlations. Okay. So this is kind of the story that will follow for the talk. We're going to first just talk about non-local games as processes on classical sets. Okay. We are then going to relabel those diagrams very quickly and say, well, this is our now definition of quantum games. We're just going to upgrade the underlying wires to be quantum instead of classical. Okay. We're then going to wave our hands a little about what strategies mean and use that to understand that a synchronous version of quantum games requires the players to work together in some way. Okay. Other than using all these string diagrams, the definition in here that's the most new is this definition of synchronicity, and it's kind of what I want to focus on in this talk. And then, if time allows us, we can talk about versions of these, examples of these games coming from like the quantum graph isomorphism game, for example. And when I say that, I mean quantum isomorphism game for quantum graphs. And we can generalize some of the classical results. Classical. Okay, so let's start. So the first thing we want to do is consider our classical set as a wire. And you can think of that as the identity map going from bottom to top on your classical set. Okay? And you can consider 4 very important operations on your set. So if you think of your set as a process, you can go from 1 copy of your set to 2 copies of your set, where you copy every element. Okay? You can take any element and delete it, just forget it existed. You can merge 2 elements, which means if they're the same, you just get it back. And if they're different, you get 0. Okay? And you can pick an element at random from your set. These are the things you can operationally do. Okay. I'm going to go back and forth in this talk between double wires and single wires. In the classical set case, this is just the Cartesian product of these 2 sets. And we're going to combine some of the set operations in order to get these useful duality cups and caps. But you can just operationally say, well, what does it mean to have this cap? It means you first merge things and then delete them. So we're just checking if it's equal or not, 0 or 1. And you can also pick a matching pair at random. So from nothing, you can generate 2 matching elements of your set. Okay. So if you've never seen string diagrams before, I encourage you to sort of keep this point of view through the entire talk and not worry about what the wires mean in the quantum case, because this is kind of a good way to think about everything. But if you have seen, for example, in quantum groups, like a co-multiplication map being represented by a diagram, then that will also help you think about these slides. Okay. So if you take that as your definition, then if you think of the usual definition of non-local games, it's some 0-1 rule matrix, and you could think of this as a map from question pairs to answer pairs, such that the map is sure idempotent, as we saw in Junichiro's talk, for example. So this just says in the classical case that this is a 0-1 matrix, okay? And this kind of additional condition, which is redundant in the classical case, but we're going to want it in the quantum case. And this somehow says that the matrix is equal to its conjugate. Okay. Okay. So that's how you define games. You can also write down the notion of a correlation, which we will also think about as a matrix or as a map from functions on your question sets to functions on your answer sets. And the entries of this matrix are going to represent your correlation values. And this linear map has to have two properties. It has to behave nicely with this deletion operation, which corresponds to summing over columns of your matrix and getting 1. Okay? And it has to be completely positive, which means that some version of your map in which you've sort of copied both questions and answers and kept track of them as well as like additional information in a new, bigger linear map. Okay, that's what this is. It's not that P should be positive, but it's that bigger composite should be positive. And that's actually equivalent to complete positivity in some sense. But in the classical case, this is just the same as saying that the entries are non-negative. Okay. And so if we have a game and a correlation, the first thing we might want to do is just say, is that a perfect correlation to play the game? Okay? So the way we can check this diagrammatically is we can take the Schur product of the matrix P with the matrix lambda. So you copy an input, a pair of questions, and you sort of apply your correlation on one side. On the other side, you apply the rules of the game, and then you check, did the game let me actually hang on to that correlation or not? And this is the same as the correlation matrix being contained in the support of your rule matrix. Okay? So this is our condition to say that P is a perfect correlation for the game lambda. Okay, so the last thing I'm going to define in the classical case is what it means for either a game or a correlation to be synchronous. So if you have any map from 2 copies of the same question set to 2 copies of the same answer set, you can say it's synchronous if it satisfies this equation, which to me says that if you have diagonal inputs, then you must get diagonal outputs. And you can read it as saying that if you take 2 inputs, merge them and then recopy, so check if they're the same, which is projecting onto the diagonal, and then you apply your map. It shouldn't matter if you check if they're the same after or not. If the answers are the same, that should give the same result. Okay, because I'm going to use this definition a lot in my talk, I have a shorthand for these sort of 2 copies of the X wire by these thick wires, and we're going to represent this merge and copy map, which you can also think of as some kind of decoherence map, if you want, for quantum information people. We're going to represent that by like a thick square on a thick wire, okay? Okay. So you can check that this is equivalent to the classical definition of synchronicity when your underlying sets are all classical. And the first thing we can check is that if you have a perfect correlation for a synchronous game, it's synchronous. This is in the classical set, okay? This is just some algebraic check. And so if we want to generalize these things to quantum games, this is one of the first facts we might want to hold if we generalize the definition of synchronicity. You might want to say that if you have some kind of synchronous quantum game, you would want the perfect correlations or quantum versions of correlations to also be forced to be synchronous. Okay. So the next thing we're going to do is we're going to take those definitions we just wrote down and say, actually, now the wires are not going to be classical sets anymore. Okay. So we have the same point of view. But now, instead of a wire representing C of x for some classical set x, we've generalized the underlying algebra to be some finite dimensional C-star algebra, if you like, or a direct sum of matrix algebras. And I'm using the terminology of thinking of this thing as a quantum set from this Musterrode-Verdun paper. It's also like in this more categorical literature, it's known as a dagger special symmetric Frobenius algebra object. Okay. But in any case, like if you like the classical picture, that's fine, just think about that. If you like the C-star algebra picture, that's fine, think about that. So we can get some similar maps. This is sort of similar to copying, deleting, merging, and generating at random, okay? But as we know, in the quantum world, you can't have a general copying map. That such a thing does not exist. And so it kind of comes as close as possible up to, maybe up to a basis. Okay. So we can just keep our same diagrams, and we can just use these as our definitions for what it means to be a game, what it means to be a correlation, what it means to be perfect, what it means to be synchronous. So I think these other definitions, game, perfect, and synchronous, are not very well studied. There are several definitions that relate to synchronicity that I won't talk about. But correlations, however, they're sort of somewhat well agreed upon. There's this idea of quantum no signaling correlations. There's this idea of quantum families of maps. These are all the same perspective. Essentially, P is the kind of channel between your C-star algebras. It's just a channel. Okay. So this is our definition of quantum games. So the first sanity check that we want, that I said we would need, is that do synchronous games force their perfect correlations to be synchronous still? And you can prove this diagrammatically. So we're going to assume that P is a perfect correlation for the game lambda. And we're going to assume that lambda is synchronous. So after this project onto the diagonal operation, we're still on the diagonal. Okay. And then you can check the same condition for P. You can notice that because P is perfect for lambda, we can add in a Schur product with lambda. Okay? There's a non-trivial equality here that shows that this projection onto the diagonal can slide only onto the right leg of multiplication, co-multiplication. It doesn't go onto the other side. Okay? There's some sort of symmetry happening there. Some other map goes on the other side, which is the conjugate of that map. Okay? And then, because lambda is synchronous, now you can apply the definition of synchronicity, that we end up on the diagonal, so this doesn't matter. And then you can use this, pulling this projection back down, and then again use the fact that P is perfect for lambda. So it's like a kind of simple algebraic proof relying on this sort of non-trivial fact. Okay, good. So far this means that we have like a somewhat reasonable definition. So now let's see what synchronous games force the players to do. Okay. So I talked about correlations, which I think about as I'll start at the bottom point over here, okay? I talked about correlations as a kind of statistical perspective of what the players are doing. And we want to think of, when I say strategies, I mean there's a more operational interpretation. There's actually some operators that the players are going to use in order to implement these correlations. And the picture here is that a correlation has this extra Hilbert space wire going into it. Sorry, not a correlation. A strategy has this extra Hilbert space wire going in and coming out that allows the players to use or measure some state in the Hilbert space. And then if you sort of take an expectation with respect to that state, you get back a correlation operator. So if you want to just write down a diagrammatic definition of strategies, you can do this kind of similar to how we defined correlations. there's going to be 3 properties, and you get something called a quantum function, which you can think of as a star cohomomorphism that's a little bit generalized. So there's some sort of entanglement assistance going on to help this thing kind of behave like a star cohomomorphism. And then if you just look at the question and answer wires being classical, then you get, and if you plug in all possible questions and answers, you get a set of operators on your Hilbert space. That's this added directed blue wire, okay? And these are just going to be, sorry, I think we actually get PVMs in this case. I think everything's a PVM, so that there's a typo there. But you're going to get a set of these operators, phi AB given xy, which are operators on your Hilbert space, that form a POVM for each pair of questions over all possible pairs of answers. Okay. This is still kind of a bad definition for strategies, though, because we actually want to enforce some kind of separation on the players. So this, you can think of this second point as more of like a template for strategies. But then if you want actual concrete strategies, like strategies that could be physically implemented by separated players, like we have in non-local games, you need to consider some different definitions of strategy classes, and you can do all of this diagrammatically. The one that I work with the most is the quantum commuting class, and that can be represented as your strategy decomposes as this kind of pair of now you have 2 quantum functions instead of just 1. And they commute on the Hilbert space leg. Okay, so now let's ask ourselves, okay, we defined perfect correlations. Can we do the same thing for strategies with this extra piece of information hanging around? Well, we can. You can take the exact same definitions and just paste on this Hilbert space wire underneath everything and not really worry about it, okay? And it turns out these give you precise and very reasonable definitions for what it means for a strategy to be perfect and for what it means for a strategy to be synchronous. We just ignore the Hilbert space wire, okay? Okay, so our theorem 1 said that when you take a synchronous quantum game and you look at its perfect strategies, they're forced to be synchronous as well. This theorem 1 prime says, oh, sorry, did I say strategies? I meant correlations. Theorem 1 prime says you could just upgrade this to strategies. And it's the exact same proof as I showed you before, just with an extra Hilbert space wire kicking around in the background. Okay, and I just put a little imprint of the proof. We just add a Hilbert space wire. Okay, so, right. So the next sanity check we want about synchronicity is that it forces the players to kind of behave in a symmetric way somehow, okay? And so in the classical question and answer case, there's some results about this in different strategy classes. So if you look, so the first result is that if you look at non-signaling correlations that are synchronous, the marginals are forced to be equal. This is a pretty simple computation that you can do, okay? And the marginals just sort of correspond to the statistical behavior of Alice, just isolated, and the statistical behavior of Bob, isolated. This second result says that when you have a quantum commuting strategy that's synchronous, the players are forced to have copies of the same POVM, okay? And so that's the non-signaling class, the quantum commuting class, and then in the deterministic case, when you just have a deterministic strategy, if it's synchronous, the players are just forced to have 2 copies of the same function from questions to answers. Okay, so we can sort of quantize all of these results. This is our theorem number 2. And it says that, for instance, if P is a non-signaling correlation that's also synchronous, and you can define non-signaling diagrammatically using the co-unit, okay? Then its marginals are equal, and they're just equal to applying this sort of like copying operation, applying your correlation, and then applying this merging operation.
Sorry, can I ask a question here about the second one? I'm a bit confused. If Alice and Bob have shared POVMs in a quantum commuting setting, doesn't that mean that everything commutes with each other?
We should talk about this later because there's been some conversation about it. Okay. So you can show that if the strategy is synchronous and it's a quantum commuting strategy, so Alice and Bob each have a quantum function, then their quantum functions are forced to be equal. And that generalizes number 2. And then number 3 says that if you have a synchronous local strategy on quantum questions and answers, you're forced to have shared correlations. But those are actually, yeah, so these are quantum functions without the Hilbert space wire, and it turns out that they're just star cohomomorphisms of your underlying C-star algebras. Okay, so this kind of says, okay, like this definition of synchronicity is kind of forcing the players to behave the same in all sorts of different strategy classes. That's good. Okay, so it looks like we have plenty of time to talk about the example. So what we're going to do is we're going to see an example of how to define a quantum-to-quantum non-local game using these diagrams and prove some nice things about it. Okay, so there's a lot of points of view on quantum graphs. We've seen several of them. This morning and yesterday, well, okay, so Junichiro's talk and Priyanka's talk mentioned this like quantum adjacency operator, which is usually the way I like to think about quantum graphs, and I actually have a slide on that in an appendix of this talk. But for the definitions I'm going to use here, it's more helpful to think of 2 other algebraic points of view on quantum graphs. One way you can think about them is as a state of your sort of vertex algebra tensored with the opposite algebra, and that state is going to satisfy several conditions. And this first condition is equivalent to the adjacency operator being a Schur projection, and the second condition is equivalent to the adjacency operator being real in the sense of Junichiro's talk. Okay. And then if you also want irreflexive, you should say that if you take your edges and you project onto the diagonal, whatever that means, then you get 0. Okay. So that's sort of the edge state point of view of quantum graphs, and then you can also think of a quantum graph as a projection that goes from your vertex algebra tensored with its opposite to itself, and it just projects any pairs of vertices onto whether they're connected by an edge or not, okay, classically. And so the quantum version of that is that this thing should be a projection. That's it. It should be a projection operator. So, orthogonal projection operator. Okay. And you can go back and forth between these 2 points of view using that the projection is the right multiplication by your graph state, and that your graph state just comes from applying your unit and then plugging that into your projection. Okay, so we're going to use both of these definitions. So the triangle is a state and the square is a projection. And using these points of view, you can define what it means for a quantum homomorphism of quantum graphs and a quantum isomorphism of quantum graphs. So the quantum homomorphism definition relies on defining quantum functions, which I didn't write down here, but they're the same types of objects that we get for strategies. Okay. So a quantum homomorphism, G to H, is this quantum function that when you kind of apply it to 2 copies of your vertex algebra, you get that it doesn't matter, like once you've projected onto edges of G, and then you've applied 2 copies of this thing to each sort of endpoint, it doesn't matter if you then check adjacency in H or not. You're already adjacent in H. And then quantum isomorphism, instead of this sort of projecting definition, you just get an intertwining condition which is stronger. Okay, and this is exactly kind of the algebraic definition of quantum isomorphism when you go back down to classical wires. Okay. Okay. So using kind of the definition of a quantum graph as this edge state, you can just write down what you might want to be your rule function for a quantum version of a graph homomorphism game between quantum graphs. Okay? So just thinking about classical graphs for intuition, what this sort of graph homomorphism rule function says is that there's sort of three cases in which you can win the game. The three cases are the following. You're adjacent in G and in H. So the questions come from vertices in G. Each of Alice and Bob sort of gets a state which is on the tensor product of vertices of G with itself. The answers are sort of two copies of vertices of H. And so either you're adjacent in G and you're adjacent in H. You're equal in G and you're equal in H. So what I mean by the square on the end of a thick wire is that I've just taken the diagonal operator and then I've applied co-units to it. So this is a usual thing to do whenever there's sort of a co-unit. You can just contract it down and ignore it in the picture because it makes the pictures more complicated, okay? But if you go to the thin wire point of view, this square, maybe I should just draw it, this sort of thick square is equivalent to just the cap. Okay. So equality in G should also mean equality in H. And then the last thing is that if you're anything other than adjacent or equal in G, so sort of unrelated in the graph G, you can do anything you want in H. Okay. And then for isomorphism, we just want to strengthen that last condition. So the third way you can win is unrelated in G and unrelated in H. So you can check that these definitions of quantum homomorphism games, quantum graphs, extend sort of like the typical homomorphism games and isomorphism games of graphs that are introduced. There's still, I haven't looked at yet whether these definitions are in agreement with some of the other like classical to quantum and quantum to classical results that are out there. Okay. But using these definitions, you can show that perfect quantum commuting strategies for the graph homomorphism game from G to H, where G and H may be quantum graphs, are exactly given by quantum homomorphisms from the graph G to the graph H in the sense that we defined 2 slides ago. And you can also do the same for isomorphism, but you need to introduce a stronger notion than strategy. You need to take that game and then play it using only bi-strategies, which sort of means you're a strategy, and in reverse, you're also a strategy. Okay, so the dagger is also a strategy. And, right, so, and then these correspond to quantum isomorphisms as defined 2 slides ago between the graph G and the graph H. And so, because we have plenty of time, I'm going to show you a sketch of the proof of Theorem 3. It relies on all of the results that we wrote down before, so it's a kind of nice way to wrap up the talk. Okay, so we're going to try to prove that just one direction. We're going to try to prove that if you have, I forget which direction we're going to show, but we'll see in a second. Okay, so the first ingredient that we need is that the graph homomorphism game, as we wrote it down on the previous slide, so that this rule function is a synchronous rule function, so we need to check how it interacts with this projection onto the diagonals operator. Okay? And so you can check what it does, and in both cases it just gives us the middle term of the rule function, which is the equality in G if and only if equality in H. Okay? So this is a synchronous game. And so then we need to do some computations. So, right, so we're starting from the left-hand side. We're starting with a perfect quantum commuting strategy for the graph homomorphism game, and we're going to show that it comes from a quantum homomorphism from G to H. So here's our strategy, okay? Because it's perfect, we can introduce like a Schur product with the rule function lambda. That's the definition of perfect. We can then expand lambda in terms of the definition on the previous, like 3 slides ago. And we get this sum of different maps applied to phi, okay? Phi like kind of contracted by various projections. But because we already showed that lambda is, because we showed that lambda is synchronous, we know that perfect strategies are also forced to be synchronous. So that allows us to delete the second and the fifth term here, because that's just the synchronicity condition that those two are equal. Okay? And then, wait, let's go back. So, and we also have 2 copies of phi here. These are the same term as well. So we can delete a lot of stuff from this equation, and that just leaves us with the equation that projection onto H, phi projection onto G is equal to identity phi projection onto G. Okay? And then we can use our theorem 2 to say that if we know we have a perfect quantum commuting strategy that is synchronous, and so it's forced to be 2 copies of the same quantum function. Okay, and this is a non-trivial result to prove, this theorem 2 for quantum commuting. But once you prove that, you can immediately write down the equation we got from up here, but replace phi with its player-by-player implementation, which is as 2 copies of the same quantum function. But this is exactly the homomorphism condition for the quantum homomorphism condition between quantum graphs G and H. Okay, so we started with a perfect quantum commuting strategy for this game, and we showed that it's exactly given by a quantum homomorphism from the graph to the other graph. And I don't know if you caught my joke there. This is a sketch of the proof because there's literally a lot of drawings in it. Okay. So let's just kind of review. I've given diagrammatic definitions of a bunch of things related to non-local games that allow you to think about quantum-to-quantum non-local games. Most of these definitions aren't really new in the sense that they agree with a lot of the other things that are out there. I'm really sorry that I didn't cite a lot of the things that are out there because I kind of mostly learned about them during this workshop. Okay? Hopefully I'll do that in future versions of this talk. The really main new definition here is the definition of synchronicity. Okay? And then there's these kind of 3 results that generalize results from the classical question and answer case. And so Peter last week gave a talk about associating quantum automorphism groups to graphs, and there was a thanks slide at the end that was drawn in terms of these graphs, and I thought it would be funny to do a similar thing. So thank you for listening. And
thank you very much. Any questions or comments?
So do you know how it relates to the notion of concurrency introduced by like Ivan, Ludmila, Mike, and Sam?
yes. So it doesn't really make sense to define concurrency for games from their perspective. It more makes sense to define them for correlations.
Yeah, sure.
But then once you're working with correlations, you have a lot more structure imposed, and you can show that concurrency and synchronicity in the biconcurrency and bisynchronicity case, so when both phi and phi dagger are concurrent or synchronous, you have a strong relationship. They sort of both imply the same thing, but maybe they're a little bit different. But in just synchronicity and concurrency, it seems like concurrency of a strategy phi or a correlation is more related to synchronicity of phi dagger, if that makes sense.
I mean, this might be a longer discussion. I'm just wondering, in the quantum foundations literature, there's been a lot of interest on like causality recently, and I'm kind of interested. There's some scenarios where formula them classically as games, and there's a very natural causal flow to these games. And in process theory literature as well, there's been interest in causality, and I don't think there's a agreed upon definition of what it means to have like a quantum strategy for a causal scenario.
Okay.
Rather than a non-local scenario.
I would be interested to be pointed to that literature.
I wonder if this can give us like some guidance on what it would mean to have a quantum strategy there.
That would be a cool connection. I don't know.
Okay, so thank you again very much.
Thank you.